Hi and Assalamualaikum. So this is our video presentation. Our topic is sustainable energy solution applying to the thermodynamics to improve the wine utilization. So this is our group members. Hi, I am Haziq. So I'm going to talk about overview of wine energy system. Wine energy systems use the kinetic energy of moving air to generate electricity through wine turbines. When wine turns the blades of a turbine, it spins a generator that produces electrical power. These systems are clean and renewable, making them an important part of sustainable energy. So we go to the next part, which is common challenge in wine turbine. First, the energy loses due to the friction and inefficiencies. Next, the natural increase of the entropy, which is limits energy conversions. Then, the difficulty in fully converting heat into work. Lastly, storing energy without significant losses. So, I'm going to talk about thermodynamic principle. For the first law, energy cannot be created or destroyed and only converted from one form to another. For the application, wine turbines convert kinetic energy of moving air into mechanical energy and then into electrical energy. This law ensures that energy is accounted for even not all of it becomes useful electricity. For the second law, it means no energy conversion process is 100% efficient and some energy is always lost as waste heat. For the application, it limits how much usable energy can be extracted from wine. Even with perfect technology, not all wine energy can be converted to useful work because of entropy increase in the system.
Now, let's look at an industrial application of wind energy. The application we're focusing on here is utility scale wind farm for power generation. So, how does it work in industry? First, wine turbine capture the wind's kinetic energy as the wine blows across their blades, and then this kinetic energy is then converted into mechanical energy by the turbine rotor. Next, the generator takes over and converts that mechanical energy into electrical energy. Finally, this electricity is transmitted via transformers and power lines to the grid where it's distributed to homes, business and industries. On the right side of the slide, you can see diagrams showing the process from wind farm to energy distribution and the inner working of wind turbine, including its components like the rotor, gearbox and generator. Here is a real-life example of a large-scale wind energy project. This is the Alta Wind Energy Center, located in California, USA. It's also known as the Mojave Wind Farm, and it is recognized as the second largest onshore wind energy project in the world. The project is designed to supply 1,550 megawatts of clean renewable energy to Southern California Edison or SCE. This supply will continue for over 25 years under a long-term agreement. In total, this forms part of 3,000 megawatt wind power development initiative, which makes it a major contributor to reducing carbon emission and advancing renewable energy goal in the region. Wind energy is a promising source of clean and renewable power, but it does come with its challenges. Let's explore 3 key obstacles and how technology offers solutions. First, variable wind speed. Wind is naturally intermittent and unpredictable. This inconsistency causes fluctuations in power output, making it hard to rely on wind energy alone. To address this, we use predictive wind forecasting. Advanced algorithms help optimize turbine operation and schedule grid usage, improving reliability. Second, we face electrical losses. During the conversion and transmission of energy, some of it gets lost, reducing overall efficiency. The solution lies in power electronics. This system boosts efficiency in converting and delivering electricity while also ensuring compatibility with the grid. Finally, blade design inefficiency. Poorly designed blades limit how much wind energy is captured, reducing aerodynamic efficiency. Through advanced turbine design, engineers now use aerodynamic blades, lightweight materials, and variable pitch blades, all of which increase energy capture and performance.
Today I want to speak about case study thermodynamic analysis of a 1.5 megawatt wind turbine. So in this case study, I analyzed the thermodynamic performance of a 1.5 megawatt wind turbine, specifically the Goldwine GW82-1500 model. The analysis focuses on a turbine hypothetically deployed in Ithaca, New York, a location chosen for its variable climate and wind conditions. The study utilized 18 years of hourly meteorological data obtained from NASA MERA 2 dataset, which includes wind speed, pressure, temperature, and humidity. The thermodynamic performance was evaluated using two key metrics. First, energy efficiency, which compare the actual power output to the total wind energy available. Second, exergy efficiency, which considers the maximum useful work obtainable by the system under ideal conditions. Using MATLAB, MAT and AB, both efficiencies were calculated, and we observed that energy efficiency consistently outperformed energy efficiency as expected due to system irreversibilities. Looking at the graph, the variation over time that wind speed is the most dominant factor affecting both efficiencies. However, temperature, air pressure, and especially humidity also had noticeable impacts. Notably, both efficiencies dropped to zero during very low wind speeds below the turbine's cut limit of 3 meters per second, and during extremely high winds above the 22 meters per second cut out threshold. Solutions and technological advancements for wind. We use thermodynamic optimizations of wind turbines. For solutions, use exergy analysis to identify energy losses in components. For example, blades, gearbox, and generator. Lastly, for solutions, minimize irreversibilities in energy conversion stages. For technological advancements, variable speed turbines like adjust rotor speed to wind speed for maximum power coefficient CP. Lastly, for technological advancements, advanced blade materials lightweight composite reduce energy loss due to inertia. Here are some words for sustainability impact, like higher efficiency equal to fewer turbines needed for the same output to less material and land use. That's all from me. Thank you.
Unfortunately, we are reaching the end, and I would like to conclude this topic. So, to conclude, wind energy system truly highlight the power of thermodynamics in sustainable technology. Thermodynamics is not just a theoretical science, but it's actively pushing the renewable energy revolution forward. A great example of this is the Alta Wind Energy Center in California, one of the largest onshore wind farms in the world, producing a remarkable 1,550 megawatts. But the future of wind energy is not only about building bigger wind farms. It lies in enhancing the efficiency of each turbine, and this is where science and innovative engineering step in. By focusing on thermodynamic optimization, we can improve the performance of turbines significantly.
So, our analysis provides a clear framework for achieving these efficiency gains and steering the global shift toward a more sustainable energy system. So, before I end this presentation, allow me to show you guys this visual. So, these 5 visuals show how wind energy works and its growth worldwide. First, the opening diagram explains how wind turbines turn wind into electricity. Next, the chart shows that wind energy production has grown rapidly over time. Furthermore, the map highlights leading countries like China, US, and Europe. Additionally, the process diagram shows how one farm delivers power to our home. And finally, the technical diagram reveals modern turbines are over 100 meters tall and can power thousands of homes. In conclusion, this proves wind energy is a proven, fast-growing, clean technology for our future. So that is the end of our presentation. Thank you for watching, guys. Bye.